Afternoon, everybody. So we're Hipster Express team. Yaomin Zhao, Matteo, Dius, me, Marco, Summit, and our mentors have been Charlene and James. So far this week, we've been trying to improve Hipster. It's already quite a parallelized code, so it's been a little bit of a challenge to try and get things going, but a little bit of background on what it is. So Hipster is a compressible fluid dynamics code. It's been around for quite a long time now. It was started by Professor Richard Sandberg, originally at the University of Southampton, but now based at the University of Melbourne. It's a high-order spatial temporal accurate code, and legacy-wise, it has MPI OpenMP parallelization, and more recently, we've moved to MPI OpenACC. I believe it's still got all the OpenMP in it, so it's possibly you could do all three, but I don't know if it would work. The code has been developed with the idea of running many different CFD sort of cases and applications. So it's actually quite a stiff code. A lot of it has been developed with pre-compiled compiler options, which makes it quite hard to optimize depending on the user case. So we've kind of got a slightly difficult case to do, because depending what people have set up the cases for, we end up with different setups of the code itself. In the case, actually, the background picture there was a compressor blade, or one of the simulations that I performed in the past. Lots of those sort of cases that we've got to. So we started by initially profiling. So it's a time matching code. So we looked at a single iteration, and tried to kind of guess or pick out areas where we think we can actually make gains. The code has already been through several iterations of GPU optimization. So as you can see, it's reasonably well optimized for GPU. We get quite a lot of compute time on the GPU already. But we picked out a few issues where we have MPI communication, so we don't have proper overlap, and we're waiting for communication to complete. And we have some computationally heavy kernels. So our idea was to look at these and see how we could potentially optimize them or improve them. Essentially our plan from the onset was to profile, program, pass out, repeat it, and we did this for 4 days straight. So we were kind of focusing on understanding the architecture of the GPUs better, understanding our code structure, and understanding different techniques. So one of the ideas was, if we looked at some of the compute-heavy modules, we have arrays where we have non-contiguous memory access. So in these operations here, we're actually pulling out memory from different sections of an array and doing the computations. So the idea was, how can we improve our loops? So initially we tried to change it to allow each thread to run its own computation, and then do the sums and add this to the array that we finally needed. But we noticed, actually, when you look at some of the compiler, what it's doing, and the implicit compiler behavior is it's generating implicit reductions. So we found out that actually by doing this and changing it to its own variable and explicitly forcing the compiler to behave in the way you want it to behave, we managed to get a 4 times speed up on accessing non-contiguous memory in this case. From that, we started to look at these large computational blocks. So a lot of the code is quite constrained by the numerics itself, so the algorithms that we require. So this can only be done in some sections. Also, originally we had it split up into different arrays. So this was a test case that we did on how we can control memory access and try and get the GPU to do as much arithmetic operations on a single chunk of memory before reading in and out. So the idea is to collect as many memory arithmetic operations that are performed on a single chunk of memory into a single loop, and then force the GPU to cache, or force it to cache the memory before doing the operations. And we found that if we restructure some of our code in this way, we can achieve a 37% speed up. We also had to play with threads and thread count to decide how much memory we're actually caching. And we found that as we adjusted the block size of the cache, we can actually get further speed up. So originally, we left this to sort of just an estimate of 32 threads per direction, and we got a 30% speed up, but after fine-tuning, we could actually increase it up to 37%. And also just as a kind of like a game. I put the whole code through a stream editor loop and changed every loop to some form of vector parallelization, which was, as a game, was quite fun, and I actually got a 2% speed up. So for about 3 minutes worth of work, 2% seemed like pretty good going. But I don't recommend it. That doesn't always work. This, while it works kind of well, we ran into the problems that actually when we start collecting all of this, it doesn't allow us to split up our kernels nicely. So we end up with issues where in this case, we actually split a very large computational kernel into several different smaller kernels in order to fill holes. So what we managed to do with trying to overlap API communications is, by doing some of the packing, sending, and then splitting up our kernels, we could fill some of the work that we were not doing before, waiting for API communications, and also reduce some of our large computationally heavy arrays by basically better access to the memory. And that actually resulted in a 25% speed up for us, which I'm not sure previously what the ratio of CPU version to GPU version is. So this on top of roughly about 24 times speed up that we got last year. So we're looking for smaller gains now, but it was interesting that we could actually still get a 25% speed up on our already ported code. And then following on from this, the problems we encountered. Originally, when we started, we had a lot of issues with the fact that our code is very stiff. That given that it's based on pre-compiler flags and the different cases that we run, we struggle to sort of shift blocks around to change the structure of the code and allow it to work for everybody. We also run into the problem with the algorithm constraints. So splitting these blocks into different kernels can be quite tricky, and so we end up again waiting for communications and things like that, and so we get quite reliant on the order of the code. We also found potentially a bug in the NVIDIA profiler when we were looking at the shared memory. It gave us metrics of 0 looking at the cache directive, so we're not entirely sure if we've optimized our shared memory tests properly. And also initially we ran into problems with module dependency. So our code was written to be based on expected features that we didn't have originally in the modules that we were using, and so we're looking at how we can make it more portable to allow it to run on any machines that we get access to. And finally, a request of, we don't know if this exists, or an OpenACC wait any directive, such that we can allow asynchronous kernels to be launched and continue once we have any of the kernels finished. And finally, wish lists. It would be nice for more tutorials for new users on some of the tools and the architecture explanation. I'm relatively new to the GPU world. Most of my previous programming has been done on CPU, so learning how to use some of the profilers and understanding the architectures. I know there's a fair bit out there, but always more tutorials are always useful. We also were curious about getting architecture specifications on the fly. So this came about from looking at managing our cache memory, and that as we change architectures, we rely on the number of threads. We managed to get a further 7% speed up just by adjusting the number of threads we're looking at, and that would be potentially quite a nice optimization to do to allow the code to do that on the fly based on the machine that you're running on. And this was something that actually came up in documentation, is that some of the more complex processes, such as cache memory directives, don't have explicit examples in the code. And finally, for the systems, we want more power. And for that, was it worth it? I think all of us think it was definitely worth it. It was really fun and a really insightful week, and I think we've all gained a lot. So, yeah, thank you very much.